few more notes on volumes of revolution. We looked in class at the case where you take some object, you break it into pieces. Those pieces are slices that are sliced perpendicular to the x direction, that being the axis of revolution. And because those are disks, in the case that we looked at before, we got to here. And then the next step was to express r explicitly in terms of x, and that, in the simple case we looked at least, was just, in the simple case, r was just equal to y, which is equal to f of x. Well, I want us to be able to get back a little bit beyond that to do some homework problems. And so, in particular, what if we had something where x wasn't the axis of revolution? What if y was the axis of revolution? And suppose I took this region in here, and I've drawn a representative strip in here. Suppose I took this region and revolved around the y-axis. And, okay, at the risk of not having enough room to do this, let me see if I can try and just double this. It's somewhere like that. It's not going to look very symmetrical, but okay. Something like that. I'm going to revolve it around, and I'll even maybe try to put in an ellipse with... I don't want it to fill. Let's see. Something like that. Okay, that works. So I'm revolving it around like this. And to make a surface of an object of revolution. And so it's going to be extremely similar. The only thing that's different is that now the thickness of the slice is dy. The variable that labels the disk slices is y. And so that's going to be an integral in y. And I'm going to want to get the radius is going to be the x value, which will be a function of y. Because here, if I tell you the y value, which tells you which disk I'm looking at, that's this distance here, then you need to tell me the radius. Well, that's in this simple case. There's other cases we'll study later, but in this simple case, that's just the corresponding x value. So let's write it out. The general formula for revolution around the y-axis. The start's going to be the same. The whole is the sum of its parts. Each part is now a slice, but with thickness dy and an area that depends on the y, the height. And if that's just a plain old disk, which we'll think about in a minute how that might be different, that's going to be pi r squared dy, and that's going to turn into, again, not in every case, but in this kind of case, that's going to be f of y squared dy if the curve is x equals f of y. So, for example, I didn't try to draw a curve that was anything reasonably plausible, but let's see, what does that look like? That looks like maybe, very roughly, that could be, in the example, it could be x equals 1 plus y minus y squared, something like that. A parabola that starts with x equals 1 when y is 0. It starts increasing when y increases, but then the minus y squared pulls it down. And I know that doesn't look like a parabola because Paint is not good at drawing parabolas. But that's the kind of thing we might have. Okay. And then we would want the integral. We would get the integral from 0 to, well, let's figure it out in a second, question mark, of pi times this whole thing, 1 plus y minus y squared, squared, because we want to turn it into the area, the pi r squared for that thing, dy. And then to get this question mark, given this function I just came up, we'd have to solve that equals 0, because that's where it comes back down to the axis. Okay, and that probably doesn't have a nice solution, but that's the solution of that would go into here. Okay, so rather than keep going with that, once you get this number, this is not a super hard integral. You'd have to just multiply it out pretty much, and you get a big polynomial. Pi comes out, get an integral. It's just kind of pi times some weird stuff with fractions and probably some roots coming from the quadratic formula. But let's look at one more case, which is if I don't actually have exactly a disk coming out. So let's erase this. Actually, I'm just going to start over. So here's the x-axis. Here's the y-axis. Suppose I had this situation where I've got one curve up here and another curve. Oops. Ooh, that's cool. Let's do that. Okay. And another curve down here. And let's join these guys with the vertical line. Okay, so there's the region I want. Maybe I'll fill that in with some paint. Boop. There's the region, and I'm going to revolve that around the x-axis. Okay, I'm going to take that and revolve it around the x-axis. That's still x there. Come on. Oh. Okay, and let's just change that to black. That can work. Okay, let's try it again. There we go. Okay, and here is the y-axis. Thank you. It's kind of slow. I think it's because I'm recording. So I want to revolve this whole thing around the x-axis. So, gosh, now I've got to copy that thing. That's pretty easy when you're doing it by hand, but let's see. So that's going to come down here, and it's going to get bowed out like that, pretty much. Let's see. Kind of like that. Oh, that's terrible. Hopefully. See, now I have to copy what I did here. Oh, goodness. What did I do there? I curved it upward, and then I curved it downward, something like that. Something vaguely like that. Forgive me for my really imprecise drawing. But at least I can fill it with the same color. Is that the same color? Whoa! It didn't like that. Oh, there was a gap. Okay. Never mind. Okay, so we're going to revolve this around. It's going to get kind of a funky shape here. It's going to have something where all these cross sections, there's a hole in everything. And so it's going to have this outer rim, and then there's a hole bored through it. So if this, let's say up here, that's y equals f of x. And down here, still got this, yeah, there we go. And down here, rather, this curve down here is y equals g of x. Then what's going to be the analog of our formula? So let's look at that. I want everything inside of the f of x, but outside of the g of x, because I want the whole bored through it. So we have to just start out our sequence. V, it's still the sum of the parts. The parts I can still slice up into, and now we're back to the x-axis being the axis of revolution. But now each part is going to be it's going to be this outer disk. Let me change back to, let me see if I can do some color here actually. It's going to be this outer disk with that as a boundary, and then the inside is going to be with that taken out. Okay, so if I look at a side view of that is just going to be a circle with a bigger circle. It's everything between there. It's going to be, doesn't look very good. That's going to be an annulus. Let's see if I can fill that with a lovely magenta color. Haha, it's going to look like that. Okay, so we just need to figure out what the area of that is going to be. Well, it's going to be pi times, let's say big R is the area, the radius of the outside, and little r is going to be the inside. And then it's going to be the difference of those two areas. And in this case, that's going to be, the pi is going to come out, and it's going to be f of x squared minus g of x squared. So we get a difference of the squares of two functions. And then we, of course, need to make that the integral from a to b, where this is going to be x equals a, this is going to be x equals b. So you get to try that on one problem, and it's going to combine some of the skills of area between two curves, like intersecting curves to figure out where you stop and start, and then this formula. instead of, notice it's still similar to the area between the curves. If I didn't have the pi and the squares here, it would just be the area between the curves. This is different, but there are similarities. So you'll have one problem where you get to try that out.